To the lecture titled Vestigial Sideband Modulation, which is part of a series of lectures related to Introduction to Communication course. So as you might remember from the previous course, we discussed single sideband modulation. And we said single sideband modulation is more efficient in terms of spectrum than amplitude modulation or double sideband suppressed carrier modulation. And the reason for that, you are using, instead of using double the bandwidth to transmit a signal with B bandwidth, you are using basically the same bandwidth, similar to the signal bandwidth. So you are not wasting much of the spectrum, but the drawback of this operation is the fact that you are introducing too much complexity to the system in order to achieve that. So now in this lecture, we will discuss and explain exactly about vestigial sideband modulation and the reason why we need vestigial sideband modulation. Isn't it, useful to use it in all the cases? Why do we need to shift to this kind of modulation? And what are the key differences from single sideband? And to which kind of applications they are applicable? So vestigial sideband will study the generation process, the detection process, mathematically and graphically and by block diagram. Basically the modulator and demodulator. And then after we finish vestigial sideband, we'll move to quadrature modulation. And in quadrature modulation, we'll explain how we can design the modulator and demodulator and see why this modulation is so desirable in communication systems. So this is basically what we are going to discuss, and it's going to be very important lecture where many of the material is going to be included in the test, the exams, and even practical life you might encounter these things. So here we go. In single sideband, as you can see here, you have your message signal, M of D. We are drawing it in the frequency domain and not denoting it as M of F. So as you can see, the signal in the frequency domain is bounded between -P and B. This is the baseband signal before you modulate it, and you want to transmit this signal to the receiver. So what do we do if we want to modulate it in single sideband? What do we do? We just take the signal itself and multiply it by a carrier. Let's say cosine 2 by FCT. And what does the carrier do to the signal? It just shifts the baseband signal to a higher frequency component, FC, positive and negative. So basically your signal here goes to the upper band and the positive one and negative one here. So this is up until here, it's double sideband and it's suppressed carrier because the carrier is not showing here. Now, if we want to transmit our signal using single sideband, we need to use a filter here. A filter that can take only this part. Yes, filter that can take either the upper side, yes, the upper side of the signal, this part, or a filter that can take the lower sideband of the signal. So in case you take the blue one, the upper side, you end up having upper sideband modulation scheme. Single sideband, but with the upper side of the signal that you modulated. In the case you are taking the lower sideband, you get a signal like this. So this and this, we call them single sideband modulation, while this double sideband. Everybody agrees on that. Now this is my modulated signal. I received it at the receiver. What do I do at the receiver? in order to be able to detect my message signal back. I just multiply it again by the cosine, by the carrier. So I multiply it by cosine 2 pi fct, and then look what happens. This, let's say that I'm focusing on this signal, yes? This part. When you multiply by cosine 2 pi fc, look what happens. This, you will see another copy of the signal at this side. Let's say this, exactly this copy, the upper side. You will one at 2fc, and the other goes here at this part. So basically it's here. So one at 2fc and one at the baseband. And when you multiply this again, the same, this will get multiplied by the cosine 2 pi fc. You get another signal, one here and another one at minus 2fc here. Okay, so to get rid of these things, of these high side, I don't need them. I just use low pass filter at baseband with this bandwidth. So when I use this filter at the receiver, I just receive my signal at the baseband. Now, this is my signal that represents the original signal that I transmitted. So basically you get this shape, but after the filter I just get this shape, which is, this is the intended message, the message that I wanted to transmit. Now, what's the problem with single sideband? Why do we need to talk about vestigial sideband? Or what was the motivation to invent vestigial sideband? The key motivation for that is the fact that when you are going to cut this signal, yes, this signal, you need to filter it, yes, you need to take one side of it, true? Now, if you want to filter it and take one side of it, what do? You filter it using a filter. But what's the characteristics of this filter? This filter should be an ideal. What do I mean by ideal? I mean by ideal that it must have a sharp edge like this and then cuts like this. But we already know from the previous lectures that you cannot design a very sharp edge filter. Yes, you can never design or be able to obtain a filter that's exactly rectangular, especially the edges vertical. The practical filters usually they have some transition at the edges. You cannot make them exactly sharp like this, because to make them sharp like this you need to, in the Fourier series analysis, you need to take from minus infinity to infinity components, and this is impossible to take from minus infinity to infinity. So what you do, you just take the most important components, and these should be not that big in order to be able to deal with them, manipulate them, and represent them. Due to not taking all the components that represent the Fourier series of the rect signal, you just take few of them, and due to taking few of them, you end up having a filter like this. Yes. So this is the practical filter, the red one. This is a practical filter. And the blue one, we call it an ideal filter, a filter that we cannot realize in practice. So since this is the practical filter, then we are going to cut part of the signal from the lower sideband and include it in the transmission. So what happens here? You don't have any more single sideband modulation. You have a new type of modulation. This new type of modulation, we call it vestigial side modulation. Vestige means portion. You take another extra portion from the other band. Unintentionally, you don't want actually, but unfortunately, because of the practical limitation of practical filter design, you cannot design it. Yes, everybody got this point. Very critical, important point to get it, to understand why do we need to use vestigial sideband sometimes, and where do we use single sideband. If you are telling us that single sideband requires an ideal filter in order to be able to practically cut the signal as sharp as you can see in the figure. But there are no sharp filters, exactly perpendicular edges. So do we really use single sideband? I tell you, yes, we use single sideband for the audio. For your when you the audio, the bandwidth of the audio signal usually does not start from zero. Let's take the spectrum of an audio signal. The audio signal usually starts like this, goes away from zero by 300 hertz, let's say 300 hertz, and then it starts appearing. And the same here, starts appearing. Okay, this is very nice for the single sideband. This is where I can apply single sideband. Why? Because when I come and design a filter which is impractical, the filter comes like this. It has transitions, not sharp edges. So it takes the whole signal. No portion of the signals from this part was taken into consideration. So practically single sideband can be used only for audio signals or for any signal that does not start from zero. But in images, in videos, the signal, the frequency spectrum of most of these signals start from zero. And for that reason, we cannot use single sideband for image or video, single sideband. So if I ask you now, give me one practical application for single sideband, where do you use it? You tell me what? Audio. Why? If I ask you why, you tell me because the signal does not start exactly from zero, or it shifts from the zero, and this shifts makes some gap between the two copies of the signal. This gap, I can utilize it to design the transition of the filter. So I am still using a practical filter and still modulating my signal successfully without taking any part from the other copy of the signal. So this is where we can use single sideband in practice. Now, when you want to transmit video or images or any other types of signals that have low component frequencies, so what do you need to do here? You need to use vestigial sideband modulation. This is the reason why we use vestigial sideband modulation. Now, this is the explanation and this is the basic introduction to vestigial sideband modulation, but let us now get into the details of the derivation and the block diagram of this type of modulation. Now, these are repetition of what I said earlier explaining on the side, but we will go over them to make sure that we didn't miss anything and you understand it. You have an opportunity one more time to make sure that you didn't miss anything and you are digesting all the information I gave to you. The upper sideband is the output of filtering signal M of t with an ideal single sideband filter. This is, we agreed on it. We said this, yes, this is the output, this is the output of this with filter, and this filter is ideal. Because why? Because you have sharp edge here. Okay? And this is the filter you define basically. Well, can you draw this filter to me? It's just this. Yes, 1 when the frequency between 0 and p, or the frequency between 0 and minus p, and otherwise. The modulated signal in single sideband at carrier frequency of fc can be constructed. Now we understand it graphically, but now mathematically, how do you do that? In time domain, it's m of t, you multiply it by carrier cosine omega ct plus minus the Hilbert transform of m of t itself, multiplied by sine omega ct. And the Hilbert transform is just the convolution of the signal itself with 1 over pi t. So this is basically Hilbert transform. And M of t is the original signal. So let's take an example about Hilbert transform so that we understand how it works. You don't need to go into the details of it, but it's basically if you have a series of rectangular pulses, rectangular signals as you can see here in the figure, the blue one. And I ask you to take the Hilbert transform. So the Hilbert transform of this is basically the summation of the Hilbert transform of this sequence. And once you find this, you take the signal, convolve it with 1 over pi t, you get this formula. This formula can be drawn in the red curve here in the figure. Now, this Hilbert transform can be used to represent the mathematical modeling of single sideband modulation, no more, no less. So it's just a mathematical trick to represent the equation of the modulation. So this is basically the single sideband in the mathematical form, and we saw it in the graphical form. Now let's go and see vestigial sideband in both math and the graphics. Yes. So first of all, the first statement explains the motivation for using vestigial sideband. It says that single sideband relies on being able to filter out one sideband. For audio, this is possible. As I just explained to you, the audio does not start from 0, starts from 300 Hertz. Because the voice spectrum drops off below 300 Hertz. You don't have frequency components of your voice below 300 Hertz. All of them, they are above that. Allowing, and this natural natural feature of your audio results in leaving some space here, some band. And I can utilize this band in order to design a filter with practical parameters. And this filter has certain transition. The transition here will not cut any part from the other adjacent signals. This is only possible and applicable for the case of audio, but this is not possible for other signals like video that have strong components at low frequencies. Video and images, they have strong components at low frequencies, which means that the signal starts immediately from 0. Images, have you ever dealt with images and you saw the frequency spectrum of images? I think if you have dealt with them or you will deal with them in the future with one of the courses related to digital image processing, you will find out that most of them, they start from 0. So the solution to this problem, if it starts from 0 and I don't have a practical ideal filter that can exactly cut the signal perpendicularly with sharp edges, the solution is to use vestigial sideband modulation, which means vestige means a small portion of the unneeded sideband signal is used. Why? Because of the shape of the filter that I use to transmit my signal. And this reduces DC distortion. Let's see how. Vestigial sideband signals are generated using standard AM or double sideband suppressed carrier modulation. We know this, nothing new. Then we pass the modulated signal through a sideband shaping filter. Now here is the new thing. The shaping filter, the sideband shaping filter is not ideal. It's with transition. How the demodulation uses either standard AM or double sideband modulation depending on whether a carrier tune is transmitted or not. So the demodulation procedure is basically very similar to the other previous modulation schemes that we talked about in the previous lectures. Vestigial sideband modulation with envelope detection is used to modulate image in analog TV signals. Why in analog TV? Because TV signal is usually composed of video and images, and the audio signal is usually modulated by FM or sometimes AM if you want to cover large distances more than 100 kilometers. Throughout the country you can transmit your signal. So far so good. Yes. Vestigial sideband spectrum. Part of the lower sideband is retained. Now let's understand this with the graphics. You have your signal M of f and you multiply it by a carrier. You take two copies of it. You will see two copies of the signal, one at the positive part of the spectrum, one at the negative part of the spectrum, and we call this double sideband. In single sideband you cut it ideally, which is impractical, but it's applicable for certain cases like audio. But here in vestigial sideband, due to using practical filter with some transition, you end up getting your signal, the modulated one, becomes something like this. Everybody can see this part. Yes, I'm highlighting it. Everybody can see this. Let me know. Yes?
Yes.
Yeah, do you see this part? This part, we call it the vestige. This is the vestige. This is the portion of the signal that you cut from the other side. Now, what happens? What's the effect of this on the modulation and demodulation? Let's see. So you need to modulate a signal while you are having this. So here we agree, this is vestigial sideband. How do you do that in processing blocks? You just M of t multiply it by cosine, and then you have hi of f. What's hi of f? Hi of f is the shaping filter. Hi of f is the shaping filter. What's the signal here? Phi vestigial sideband of t. It's actually M of t. It's, if you want to write it in the frequency domain, M of f shifted due to being multiplied with cosine, shifted by fc at positive and negative. So M of f plus fc plus M of f minus fc. And then you multiply it by the shaping filter in the frequency domain, hi of f. So this is the mathematical formula or notation, the mathematical equation of the vestigial sideband modulation scheme. This is by math, this is by drawing, this is by block diagram processing. This is the transmitter at the modulator. What about the receiver? You take the signal as normal and then you multiply it by a carrier, cosine omega ct. Then after you multiply it by a carrier, you take two copies, one copy around the baseband and the other copy around 2C. 2C, to get rid of the copy at 2FC, you just use low pass filter. And this low pass filter is specifically designed to be able to recover the vestigial sideband signal. So it's not like the regular normal low pass filters. Let's see what's special about this filter. Here is the filter. So the filter H naught of f should be 1 over hi of f plus fc plus hi of f minus fc, where magnitude of f is bounded by the bandwidth b. So here E of t, you understand that it's coming from multiplying the vestigial sideband with the cosine omega ct. Yes? And in the frequency domain, it looks like this. This is the formula in the frequency domain. You just shift plus fc minus fc. And in order to recover the original signal, we must use a specially designed shaping filter called H naught of f, which is the opposite, the inverse of hi of f. And this is how you design it. This is a low pass filter, that's the inverse of hi of f. in order to remove the effect of this. The effect of this vestige. You remember the effect of this vestige. Let's see how this happens graphically. So you have your HI of F. This is the shaping filter that you used in order to send your signal, yes? Let's say your signal is something within this region, yes? And the vestigial sideband, due to the transition, you take some additional part. Yes, this belongs to the filter, this belongs to the signal. Now you have the same here. When you multiply by, at the demodulator, multiply by cosine 2 by fc, you get one copy at the baseband and one at the high frequency spectrum. So we take care of the one near the baseband, and when you draw the signal around baseband, let's see together what happens. So you have the first one, this is the first signal, yes, copy of this, but at the baseband, and you have the second signal, which is like this. Sorry, this is the second signal. Yes, everybody agrees on that. Now these signals are coming in this region. Let me draw this region to you. This region. The two signals are coming on top of each other. They are kind of interfering. What will happen if two signals are on top of each other? What happens mathematically? What do? You sum them. Yes? You sum them. So sum this at this point. 0 plus this value. It's this value. This plus this value. It's this black one here. This plus this, it's this. This plus this again, it's this value. So when you sum all the points coming from the first signal and the second signal, you end up what? You end up having a total signal of this amplitude. Yes? This is coming from the summation of the vestige parts of each of these two signals. Clear? So now what do you have? This is the shape you have. What do I have in the formula of the filter, shaping filter? I have 1 over that. 1 over that. So when you say 1 over that, what do you do? What will happen? This, the lower one here, this will become higher, and this will become lower. So you get a shaping filter similar to this, and you go down, of course, until you reach. So which is practically this one. So this is the filter you need to use at the receiver so that you can reconstruct your signal successfully. Let's now take numbers. So this what's the value here? Half, yes. At this point, everybody agrees with me, this is half. This filter is 1 over the value here. 1 over half equal 2. So this is the 2. So all the whole signal within this duration or within this bandwidth takes the value 2. And what's the value of this signal? 1. 1 over 1, 1. It remains 1. And then you draw it. Clear? So this is the filter that you need to use at the receiver in order to reconstruct your signal successfully. Now the advantage of vestigial sideband. Using vestigial sideband instead of double sideband modulation saves about 3 megahertz. Yes, it's similar to single sideband kind of, but you save bandwidth compared to double sideband, and allows a carrier tone to pass. Yes, because it takes additional part from the signal, from the other part. So if you have a carrier in the middle, the carrier will pass. But in single sideband, the carrier cannot pass usually. And the shaping filter satisfies this equation. Now let me ask you one question. If I say that up until now we have double sideband, yes, modulation, we have single sideband, and we have vestigial sideband. And I ask you, which one of these modulation schemes is the most spectrally efficient modulation? Means it takes minimal bandwidth to transmit your signal. Which one? The most spectrally efficient. Which one of these modulation schemes? Can you please let me know? Let's say this is 1, this is 2, this is 3. 1 or 2 or 3 is the most spectrally efficient. Yes? Any answers? To me, it's single sideband is the most spectrally efficient one. Do you agree with me? Do you agree that single sideband is the most spectrally efficient modulation scheme? Yes or no? Single sideband is the most spectrally efficient. Why? Because for a message with bandwidth B, yes, you require a modulated signal of bandwidth B. So this is number one in terms of spectral efficiency. But at the expense of what? What's the cost here? Complexity. Complexity, single sideband is the most complex modulation scheme, analog modulation scheme among the others. Now, vestigial sideband is the second one in terms of spectral efficiency because it's like single sideband but takes another part, like an extra part from the adjacent signal. So this is the second most efficient one, and double sideband is the least efficient modulation scheme. So we agree on this. You got it? So if you have understood vestigial sideband and double sideband and single sideband modulation, which are the three of the most fundamental and basic analog modulation schemes in communication system, I expect from you to be able to draw them in frequency domain, the signal, the modulated signal, demodulated signal, and the signal after filtering in time and the frequency, be able to process the signal at the transmitter and receiver and show and draw the block diagram and how do you generate the signal graph by blocks, and also deal with it mathematically. What's the mathematical formula of the signal in double sideband, the mathematical formula of the signal in single sideband and vestigial sideband at the transmitter and receiver at different stages of the block diagram. So I can tell you at this part, what's the signal here? Could you please draw the signal to me here at this part, at this point? At this point, could you please draw the signal to me? Could you please give me the mathematical equation to that signal? What are the key advantage of this modulation scheme? Why do we use this modulation scheme? And why is it better than single sideband, for example? For which applications we can use this modulation scheme? Why cannot we use vestigial sideband? Why cannot we use single sideband modulation for video, for example? You must be able to answer all these questions, and not answering them by memorizing them, but by understanding them and base your answer on knowledge and reasoning of why this is happening. So once you get full understanding and full comprehension of the math, the graphical representation, and the block diagram processing, then I believe you are comfortable now and kind of knowledgeable in the analog modulation schemes. So we stop here and we continue after 5-10 minutes in the second part called QAM modulation, quadrature amplitude modulation. Thank you very much for your attention and see you in the next lecture.